The next physical property to discuss is about the electrical conductivity. The electrical conductivity of structure of metals are as such. For ionic compounds are generally good electrical conductors in the liquid and the aqueous state, but not in the solid state. Simple molecular structures or simple molecular covalent compounds are non-electrical conductors in all states, similarly to your macromolecular structure with the exception of graphite. Your metallic structures are good electrical conductors in the solid and liquid state. So what constitutes electrical conductivity? A substance is a good electrical conductor only when it has mobile charged particles that can act as charge carriers through the substance. So for ionic structures, it's observed that ionic compounds are able to conduct in the liquid or aqueous state because they consist of mobile, oppositely charged ions and can act as charge carriers, as opposed to ions in the solid lattice, where ions are not mobile and therefore they cannot act as charge carriers. This is the reason why ionic compounds are only able to conduct electricity only in the molten or aqueous state. For a detailed animation, you may refer to the following URL.
Let us discuss about the electrical conductivity of macromolecular structure, in particular diamond. In diamond, it is a covalent network structure. Typically, they are not electrical conductors because there's no uncharged particles which are able to carry charge. Each carbon atom in diamond is bonded to 4 other carbon atoms, and therefore all the valence electrons are used up in covalent bond formation, leaving behind no mobile charge carriers to carry charge. On the other hand, graphite is able to conduct electricity in the solid state. This is because of the different structures of graphite as compared to diamond. Each carbon atom in graphite is bonded to 3 other carbon atoms, which leaves behind a 4th electron that is delocalized over the whole of the layer of atom in graphite. These delocalized electrons are no longer associated directly with any atom or pair of atoms, but they are free to travel throughout the whole layer, therefore acting as mobile charge carriers. Last but not least, let us discuss about the electrical conductivity of metals. Metals are good electrical conductors even in the solid state. This is because they consist of mobile valence electrons that serve as charge carriers throughout the metallic solid. Last but not least, the last physical property to discuss is about solubility. Please note that solubility of the solutes in various solvents can be explained in terms of the relative strength of intermolecular forces, and this will be covered in CM3108 in the next semester. Ionic compounds are generally soluble in water, but they are insoluble in non-polar organic solvent. Your simple molecular structure, on the other hand, are generally insoluble in water but soluble in non-polar organic solvent, with the exception of hydrogen chloride and ammonia, which are polar covalent compounds. Your macromolecular structures are generally insoluble in water as well as in non-polar organic solvent. This is also the same for your metallic structure. Last but not least, I would like to round up today's lesson with a short discussion about amorphous solid. What exactly are amorphous solid? So far, the different structures that we have discussed are all regular arrangement of atoms in a 3-dimensional lattice. Solids, for example, like glass, polymers like plastics, nylon, polyethylene, usually do not have a regular structure at the molecular level. These are otherwise known as your amorphous solid. For example, quartz, your silicon dioxide. In fact, it's a crystalline network covalent structure constituting to your macromolecular structure. But when it melts and is then rapidly cooled, the atoms are unable to return to an orderly arrangement. This resulting amorphous solid is then known as glass, which does not have a definite melting point that is characteristic of pure solid. Instead, glass softens over a temperature range. So as seen in the schematic over there, you can see that silicon dioxide in quartz are arranged in regular arrangement, giving rise to its crystalline appearance. Silicon dioxide in glass, on the other hand, are not regularly arranged. In the round-up to this e-learning module, I would like to conclude today's lesson with a DIY practice. Can you spend the next 5 minutes trying to answer this DIY practice? Element X and Y form chlorides XCl2 and YCl2. Some of the properties are listed as below. XCl2 has relatively low melting point and boiling point in comparison to YCl2, and it does not conduct electricity in the liquid state. First question, what is the physical state of each chloride at room condition? At room condition of 298 Kelvin or 25 degrees Celsius, the room temperature lies between the melting point and boiling point of XCl2, which means that XCl2 should be a liquid at room temperature. In comparison, the room temperature is way below the melting point of YCl2, and therefore YCl2 will be a solid at room conditions. State represents the type of bonds in XCl2 and YCl2. XCl2 is most likely a covalent compound. To be more exact, it has a simple molecular structure. This can be observed by its relatively low melting point and low boiling point, and its electrical non-conductivity in liquid state. On the other hand, YCl2 is evidently an ionic compound. This can be confirmed by its high melting and boiling point as well as its electrical conductivity when it is in the liquid state. With this understanding, X is most likely a non-metal because X form covalent compounds with halogens. From the molecular formula of XCl2, element X is most probably in group 6. Since Y form an ionic compound with a halogen, Y therefore must be a metal. And from the molecular formula of YCl2, it implies that Y is most probably in group 2 of the periodic table. To draw a structure to show the arrangement of valence electrons of atoms in the molecule of XCl2, we know that X is in group 6, and therefore it has 6 valence electrons. Chlorine, which is in group 7, will have 7 valence electrons. So by drawing out 2 chlorine molecules, we realize that it will form 2 single XCl bonds, with each of the chlorine atom forming covalent bonds. Last but not least, would you expect XCl2 to be soluble in water? What about YCl2? Explain your answer. Personally, I would think that XCl2 to be insoluble in water. This can be explained by XCl2 being a covalent compound, and since X is in group 6, they should have similar electronegativity value as that of chlorine. Hence, it is very likely that the bonds of your XCl are non-polar. Since the bonds are non-polar and based on the light dissolve light rule, XCl2 is unlikely to be soluble in water. YCl2 on the other hand will most likely be soluble in water. This is because YCl2 is an ionic compound. In addition, your group 2 metals chlorides are soluble.